there are many theorems known as central limit theorem or abbreviated as CLT, as for example Lindberg Levy theorem, Lyapunov's CLT, Lindberg-Feller CLT, and so on. There are many other theorems that actually considers the case when x1, x2, xn are not really IID or independent. In fact, there are some theorems that deal with some dependent random variables, but that is not really the major point of our discussion today. So today we will discuss only a few examples of CLT, how it behaves, and under what condition we can say that a CLT holds. So it is important to note that a CLT can hold only under some specific conditions. So we will discuss these things through some examples. Another interesting feature that we would like to discuss today is that it is not true, although it is a very common notion that somehow some of the random variables usually follows normal distribution. That is not always true. So we will discuss one example where we will show that the CLT exists, the sequence of random variables converges to a distribution, converges to another probability distribution, but that is not really a normal distribution. So in that sense, this example is a very interesting one, and it actually indicates the non-universality of normal probability law. Before discussing some examples of CLT and maybe some of its implications, we will first state a few central limit theorems that eventually we are going to use. The first one is Lindberg-Levy theorem. Let us suppose that Xn is a sequence of independently and identically distributed random variables such that expectation of xk equals to 0 and variance of xk equals to sigma squared, which is less than infinity. That means here we are assuming the existence of second order moment of each of the random variable considered in this case. Now define Sn equals to summation xk, that is sum of n random variables. Then as n goes to infinity, that is number of observations or number of variables goes to infinity, then Sn by sigma root n goes to tau, that means tau follows normal 0, 1 in distribution. So this states the convergence in distribution of the sum of random variables normalized by its variance as expectation is 0. Now if we relax the condition that the random variables are identically distributed, in this area we are stating another CLT which is due to Lyapunov's, known as Lyapunov's central limit theorem. The statement is as follows: let Xn be a sequence of independent random variables but may not be identical, such that expectation of xk equals to 0, expectation of xk square equals to sigma k square, which is less than infinity, and we define small Sn, which is sum of the variances, that means summation sigma k square, k equals to 1 to n, and we assume another condition which is known as Lyapunov's condition, which is summation k equals to 1 to n, expectation of modulus of xk to the power 2 plus delta by Sn to the power 2 plus delta. This goes to 0. For delta lies between 0 and 1, delta is 0 less than delta less than equals to 1. Then it can be shown, actually we have already shown this in a previous talk, that sum of the random variables normalized by its variance, that is capital Sn, which is summation xk k equals to 1 to n, divided by small sn, that is summation sigma k square k equals to 1 to n. This goes to tau in distribution as n goes to infinity, where tau we know that as a standard normal variable. Note that Lyapunov's CLT assumes the existence of moment of order slightly higher than 2. Now, but the important thing is that in the expression of the main theorem, that is the random variable or the normalized variable for which we are investigating the convergence in distribution, only the term sigma appears or sigma square appears. That means that in the formulation we are using the moments up to second order, but in order to prove this CLT we are assuming the existence of slightly higher order moment, higher than 2. So Lindberg and Feller came up with another theorem that is actually assuming the existence of only up to second order even when we are assuming the independent random variables. So the statement goes like this: if xn is a sequence of independent random variables with the expectation of xk equals to 0, expectation of xk square equals to sigma k square, which is less than infinity, and Sn equals to variance of capital Sn, which is equals to summation sigma k square, k equals to 1 to n. Then again the normalized sum, that is capital Sn by small sn, converges in distribution to tau, a standard normal random variable, and maximum over k lies between 1 and n of sigma k by Sn goes to 0 as n goes to infinity. If and only if for every epsilon greater than 0 and fk being the distribution function of xk, we have gn epsilon equals to Sn to the power minus 2 summation k equals to 1 to n integral of x square dfk over the set modulus of x greater than equals to epsilon small sn. This quantity, that is gn epsilon, goes to 0 as n goes to infinity for every epsilon greater than 0. So this is basically both a necessary and sufficient condition. Now we will first prove one very important lemma. This lemma looks trivial, but let us consider the proof here in a formal way. The lemma is that states that for a sequence of uniformly bounded independent random variables, a necessary and sufficient condition for the CLT to hold is Sn square goes to infinity as n goes to infinity. Now suppose if possible, because we have to show that Sn square goes to infinity, in fact this is a necessary and sufficient condition. So if possible, let us assume limit Sn square as n goes to infinity is less than infinity, that means it's a finite, and Lindberg's condition holds. Then Sn square goes to capital B square, so some b for some b. Then for any fixed j, we can find an epsilon greater than 0 such that probability modulus of xj minus mu j greater than epsilon into capital B, which is greater than 0. Then for n greater than equals to j, Sn to the power minus 2 summation k equals to 1 to n integral over mod x minus mu k greater than equals to epsilon Sn x minus mu k square dfks greater than equals to epsilon square summation k equals to 1 to n probability modulus of xk minus mu k greater than epsilon Sn, which is greater than equals to epsilon square into probability mod xj minus mu j greater than epsilon into b. Now we know that probability the last term is greater than 0. So Sn to the power minus 2 into summation k equals to 1 to n integral over mod x minus mu k greater than equals to epsilon Sn x minus mu k square dfk x, there is a left, there is a quantity in the extreme left, this is greater than 0, which actually violates the Lindberg's condition because we have assumed that Lindberg's condition holds. So here is a contradiction. So Sn square cannot be less than infinity. That means we get that Sn square goes to infinity as n goes to infinity is a necessary condition. So this proof is basically by something what is known as proof by contradiction. Now alternatively, if we take the quantity summation k equals to 1 to n xk minus mu k by Sn equals to x1 minus mu1 by Sn plus 1 by Sn into summation k equals to 2 to n xk minus mu k. If we assume that CLT holds, then the second term on the right hand side must converge to a standard normal variable, that is normal 0 1, but the first term is a bounded normal random variable. So it is clear that Sn square must go to infinity as n goes to infinity. So since Sn square goes to infinity, we just take Sn to be arbitrarily large, that means Sn greater than 2c by epsilon if n is large enough, that is epsilon Sn greater than 2c. Also, modulus of xk minus mu k less than equals to 2c, because we have assumed the boundedness of the random variable. So there exists an n epsilon such that small n greater than equals to capital N epsilon and modulus of xk minus mu k less than equals to epsilon Sn for k equals to 1 to up to n with probability 1, we have summation k equals to 1 to n integral over the set mod xk minus mu k less than equals to epsilon Sn of xk minus mu k whole square dfk equals to variance of Sn, which is equals to small sn square. This is because the variables are assumed to be bounded in this case. So, if we divide both sides by Sn square, the left side would be equals to 1, and 1 because we are taking the integral over modulus of xk minus mu k less than equals to epsilon Sn. So, if we consider the integral of greater than modulus of xk minus mu k greater than epsilon Sn, this should go to 0. This should be equals to 0 in fact. So, Lindberg's condition is trivially satisfied, and so that is the proof of this lemma. So, this lemma is very important. So, whenever we have a sequence of uniformly bounded but independent random variables, we just want to check that some of the variances of the sum, that means summation sigma k square or Sn square, if it goes to infinity, as n goes to infinity, then we can immediately say that the CLT holds. So, this is a very nice condition, very simple condition to check, but provided these conditions in the lemma must be satisfied, that is the boundedness and independence. Now, we consider one example. Suppose xn is a sequence of independent random variables with probability xk equals to plus minus k to the power delta equals to half. That means probability xk equals to k to the power lambda equals to probability xk equals to minus k to the power lambda equals to half. Now, then weak law of large number holds if and only if lambda less than half, and CLT holds if and only if lambda greater than equals to minus half. Here we are not going to prove why weak law of large number holds for lambda less than half. This is very easy to check. So, we only concentrate on the CLT part. First take k greater than equals to 1, and then a little bit of algebra, a little bit of manipulation will show that mu k, which is expectation of xk, equals to 0. And sigma k square, which is variance of xk, which is nothing but k to the power 2 lambda. So, let us calculate Sn square. Now, Sn square equals to 1 plus 2 to the power 2 lambda plus 3 to the power 2 lambda and so on up to n to the power 2 lambda, which we can approximate for large n as 0 to n x to the power 2 lambda dx, which is equals to n to the power 2 lambda plus 1 by 2 lambda plus 1. So, what is Sn square by n square? This is equals to 1 by 2 lambda 1 by 2 lambda plus 1 into n to the power 2 into lambda minus half. Now, again n to the power 2 into lambda minus half goes to 0 if lambda less than half, because if lambda is less than half, then n to the power would be negative. So, it goes to 0 as n goes to infinity. So, we can say immediately that Sn, so what is Sn square? So, Sn square is now n to the power 2 lambda plus 1 by 2 lambda plus 1, and mod xk is less than equals to n to the power lambda for every k lies between 1 and n. So, Lindberg's condition holds if epsilon Sn, which is approximately equals to n to the power lambda plus half by 2 lambda plus 1 square root of that into epsilon, this quantity is greater than n lambda. So, after a little bit of manipulation, we have n to the power half is greater than square root of 2 lambda plus 1 into epsilon to the power minus 1, or n greater than 2 lambda plus 1 into epsilon to the power minus 2 greater than 0 holds. Now, this requires another condition, that is 2 lambda plus 1 must be positive. That means lambda must be greater than minus half. So, Lindberg's condition holds if lambda greater than minus half, and in that case CLT will also hold. So, we have proved that CLT holds if and only if lambda greater than minus half. So, we will consider the case when lambda equals to minus half separately, although which is very easy. So, if lambda equals to minus half, then Sn square equals to 1 plus 1 by 2 plus up to 1 by n. That means Sn into epsilon equals to square root of log n into epsilon. And we also know that modulus of xk is bounded for k equals to 1 to n. So, the lemma applies here again, and that actually completes the proof. Now, we will discuss one very interesting but an important result or important example in the context of this CLT or central limit theorem, which is known as non-universality of normal law. That means, although we have a notion that whenever we have some kind of normalized sum, or if we want to investigate the behavior of a statistic for when the sample size is very large, then as n goes to infinity, this random variable goes to a normal distribution, or rather converges to a standard normal variable in distribution, but that is not always true. This example will clarify this thing. Suppose x1, x2, etc. Be a sequence of IID random variables. So, here we are considering a very simple thing. The random variables are all independent and they are identically distributed. But the PDF is fx equals to half into e to the power minus mod x when x lies between minus infinity to infinity. That is the entire real line. Now, this distribution is known as double exponential distribution or Laplace distribution. It is clear that expectation of xk equals to 0 and for every k greater than equals to 1, and expectation of xk square equals to 2. Now, the characteristic function of xk can be calculated, and it is seen that phi k theta, which is the characteristic function of xk, is nothing but 1 by 1 plus theta square. Now, let us consider a new random variable as y, which has the same distribution as the random variable which is defined as 2 by pi into x1 plus 1/3 x2 plus 1 by 5 x3 plus and so on, which is equals to 2 by pi summation k equals to 1 to infinity xk by 2k minus 1. So, this is the random variable that we are considering, and we will investigate the limiting distribution of this variable. We assume that this has the same distribution as that of y, where y is a new random variable. Now, let us define zk as 2 by pi into xk by 2k minus 1 for k greater than equals to 1. Then it is clear that Sn equals to z1 plus z2 plus zn, and that converges to the random variable y in distribution as n goes to infinity. That is the way we have defined this zk and y. But remember, this holds because 1 plus 1/3 square plus 1 by 5 square, which is up to infinity, is an infinite series, which is equals to pi square by 8, and expectation of Sn equals to 0, variance of Sn is approximately equals to 1 as n goes to infinity. Now, we have also assumed that xk are IID distributed, IID random variables. So, naturally zk is an independently and but zk is independent. So, remember, although xk's are IID, but zk's are independent but not identically distributed sequence of random variables. So, again, since they are independent, we can easily calculate the characteristic function of Sn, which is in fact phi of, let us denote it by phi of third bracket n theta, which is equals to phi 1 2 pi by 2 theta by pi into up to phi n 2 theta by 2n minus 1 into pi. And if we simplify this thing, if we expand this thing, we will get 1 by 1 plus 2 square theta square by pi square into 1 by 1 plus 2 square theta square by 3 square pi square into 1 by 1 plus 2 square theta square by 5 square pi square up to 1 by 1 plus 2 square theta square by 2n minus 1 whole square pi square. And it can be shown that by resulting analysis which is known as Gregory's series that this goes to or this converges to 2 into e to the power theta plus e to the power minus theta whole to the power minus 1. So, although this looks little complicated, but if we do stepwise, it is very simple. Just calculate the characteristic function of the random variable, which is Sn, which is the sum of n random variables that which are zi's, that is z1 plus z2 plus zn, and this characteristic function actually converges to another function of theta, which is 2 into e to the power theta plus e to the power minus theta whole to the power minus 1. In fact, this thing is also a characteristic function. So, the characteristic function of the limiting random variable in this case, which is y, which is equals to phi theta, that is limit n goes to infinity, phi third bracket n theta is equals to 1 by cos hyperbolic theta. Now, by inversion theorem, we can easily get the PDF of y, because we know that continuity theorem of characteristic function and uniqueness theorem of characteristic function, and also applying inversion theorem, we can get the distribution of y, rather the PDF of y, which is seen to be f of y equals to 1 by e to the power 1 by 2 pi y plus e to the power minus 1 by 2 pi y. In fact, this is the PDF of a logistic distribution, or which is known as logistic PDF, which means that here we get the limiting distribution in the sense of convergence of distribution or convergence in law of sum of random variables is not a normal distribution. So, this example is a very interesting theorem, and it is a unique thing in the sense that it deviates the limiting random variable is not really a normal distribution. Today we have discussed a few examples and a very important lemma relating to the central limit theorem or CLT. This lemma actually gives us some condition under which CLT holds, and this would be very useful in other problems also. Moreover, we have discussed a few examples, and more specifically an example where we should have shown that a particular sequence of random variables that really converges to a distribution to a random variable, but that random variable has a distribution which is other than normal distribution, and we have naturally used the characteristic function and inversion theorems to prove this. So, in that sense, this example is a very important one in the study of limit theorems, which ensures that it is not true that everything or every sequence will converge to a normal distribution. There exists some sequences which may not converge to a normal distribution. So, in that sense, this example is an extremely important one, and that shows that normal law may not be treated as a universal thing.